Welcome. Today we are going to discuss about limit and continuity of function of two or more variables. Before we start, let's start with the following quote. With me, everything turns into mathematics. So this is a quote by René Descartes. Descartes was an important mathematician, philosopher, scientist of his time. So one of the things we might know about Descartes' work is Descartes' rule of sign, which is used to find out how many zeros does a polynomial, a real polynomial has. So let's get back to limits and continuity. So recall, what does it mean by f has limit? So limit as x goes to a, f of x equals to L. Yeah. So if you drew the diagram, this is how it looked like. So at a, you had the following, more or less the following structure, that you can make f of x close to f of x can be made close to L by taking x close to a. Yeah. So this was the idea of limit in function of one variable. We want to generalize this idea to function of two variables, and later on you'll see that this can be generalized to function of n variables in a similar manner. So first of all, what is the limit of function of two variables? So let's start with the function f. So let f be a function of two variables whose domain is D, which includes points arbitrarily close to AB. We say that the limit of f of x as x approaches AB is L, provided that given epsilon greater than 0, there exists delta greater than 0, such that if x and y is a point in the domain of f such that x minus a, y minus b, x minus a square plus y minus b square root is less than delta greater than 0, then f of x y minus L is less than epsilon. Huh. Okay, so how do we make sense of this? This means that if xy, distance of xy and AB is less than delta, then distance of f of xy minus, so distance of f of xy, because f of xy is a real number, the distance between f of xy and L is given by less than epsilon. Now, since we want since there's a possibility that the function is not defined at AB, we have distance between them greater than this implies is less than epsilon. So how do we start? We say, well, we can make f of xy close to L. How close? The close we want by finding a delta. That moment you take x minus y, sorry, the moment we take xy at delta distance from AB, then f of x minus L is going to be less than epsilon, or distance between f of x and L is going to be less than epsilon. So if you write this in the distance formula setup, this is going to be x minus a square plus y minus b square. This is a distance formula. So this is less than delta greater than 0 implies f of x minus L is less than epsilon. Okay, so let's start it again. So you start with an epsilon greater than 0. Then for this epsilon, you can find delta such that, again, distance of xy with AB is less than delta implies f of xy minus L is less than epsilon. And the notation for this is limit as x goes to AB, f of x is L. Okay. And roughly it means whenever xy is close to AB, f of xy is close to L. All right. So if you want to look at from the diagrammatic perspective, this is AB. This point is AB. So you are saying limit as xy goes to AB is f of xy is L. It means what? It means the moment you are close to, if your x, y are point here, then f of xy's will be point here and they will be in less than, they will be what, at distance less than epsilon from L, right? So if you are between this interval, then you are less than distance epsilon from L. Okay. So this is the definition of limit. Okay. So note that you had the following for a function of one variable. So if you had a, you could say that the limit does not exist since the left-hand limit at a is not equal to right-hand limit at a. Or in other words, if this is my function f of x, then limit x goes to a plus f of x is not equal to limit as x goes to a minus f of x. Therefore, this implies limit x goes to a does not exist. So there were only two sides to approach to a point, but in function of two variables, it's slightly tricky. Why? Because you are looking at a point A, B. So A is here, B is here. So you're at point A, B. So this is your domain D. So let this be part of domain D. Now, there are so many different paths to go to AB, right? So if the limit f of xy as xy goes to AB, L holds, then it must hold along every path or every route. Okay. Or in other words, if you want to show that the limit does not exist, similar to here, what you need to do is you need to show that f of xy goes to L1 as xy goes to AB along some path C1, and f of xy goes to L2 along some path C2 as xy goes to AB, and if L1 is not L2, then the limit does not exist. So this is the idea behind proving that the limit does not exist. So let's see an example. So if you draw this graph, this is sine x squared plus y squared divided by x squared plus y squared. So this is how the graph looks like. Of course, at 0, it is not defined. So there's a hole here. Yeah, because at 0, you're defining by 0, so it does not exist. Now, no matter what path you take to go to 0, 0. So 0, 0 lies below here. Yeah, it's inside 0, 0. No matter what path you go in the domain, in the xy plane. So let this be your x, this be your y. Yeah, this is your z. So no matter what you go, whichever path you take here, on the top of the function will be somewhere here. You will still approach. It's going up like a hump to get to 1. Yeah. So you see, if you go to 0, 0 in the domain, which is the xy plane, your function basically is going up to what value? 1. Even here, if you take a path going to 0, 0 along here, your function will follow the path, still get to what value? 1. Even here, yeah, it goes to 1. This value is 1 if you're moving along this path to 0. So what I'm saying is the following: if xy goes to 0, 0, your f of xy goes to 1, no matter what path you take. So it seems that the limit is 1 in this case. Although this is not enough as a proof, we'll need more tools to prove this. Let's take another example, namely x squared minus y squared upon x squared plus y squared. So this is how the graph looks like. I have drawn it on GeoGebra. You can use Desmos to also draw this graph. So what about this graph? So as your x, so let's see. So let's take one path, which is, so let this be x-axis, this be y-axis, and then by right-hand rule, this is z-axis. So if your x is going to 0, so you are going xy goes to 0, 0, along x-axis. So if you go xy goes to 0, 0 along x-axis, so this is your domain, point xy going to 0, 0. Now what is happening to the function? So the function values lie here. They are going to, f of xy is going to be, its constant going to -1. Similarly, if xy, so we see that along x-axis, so this is your x-axis. Similarly, if xy goes to 0, 0 along y-axis, so if you're going to 0, 0, that is now your domain is this is the point in the domain. Your f of xy is on the top. It's going to 1. If you're going from this direction as well, it's going to 1. So you see, as xy goes to 0, 0 along y-axis, f of xy goes to 1. So along two paths, the limits are different. Therefore, limit as xy goes to 0, 0, xy goes to 0, 0, f of xy does not exist. Because if this limit exists, it should be independent of the path. Okay, so let's formalize this. So let's prove this now algebraically without a diagram. So so let's look at the following problem: evaluate the limit or show that it does not exist. So as we saw up here. So we will write down the same thing here. So limit as xy goes to 0, 0 of f of xy along x-axis is going to be limit as xy goes to 0, 0. We'll have what along x-axis, what is the y? Y is 0, right? So which you will get x0 minus 0 square, x square plus 0 square. And that is going to be 1. Yeah, along y-axis. So that is y is 0, right? Similarly, limit as xy goes to 0, 0 of f of xy along y-axis is equal to limit as xy goes to 0, 0. Now along y-axis, x values are 0, right? So if you look at this, along y-axis, if you're going to 0, 0 along y-axis, here all the x values are 0, right? So it is going to be x equals to 0, x 0 square, 0 square, because x is 0, so 0 square minus y square upon x square, so 0 square plus y square, that is going to be -1. So we can say since limit depends on path, it does not exist. Yeah. So if limit exists, it should be independent of the path. Okay. Now there's another way to write down the same result. We can do the same thing in the following way. Now limit xy goes to 0, 0, f of xy along y equals to mx, right? Because that's the path which goes to 0, 0. You're going along the line y equals to mx is going to be limit as xy goes to 0, 0. Now instead of y, I'm going to write mx. So I get x square minus mx square upon x square plus mx square. Take x square common. So we get limit as x goes to 0, xy goes to 0, 0, my bad. Xy goes to 0, 0. Take x square common, 1 minus m square upon x square, 1 plus m square. That is simply 1 minus m square upon 1 plus m square. I can cancel out x square. So this depends on path. This is the limit, which depends on path. Path. Actually, it depends on m, which defines the path. Therefore, limit does not exist. Okay. Now note that it cannot be, need not be just linear path. It could be paths. Okay. All right. So now what about this guy? Limit as xy goes to 2 minus 2, 4 minus xy times 4 plus xy. You want to see what is this limit. So this is your point, say 2 minus 2. Yeah. So let's consider the following path. So this, so along y equals to minus x. Yeah. So along y equals to minus x, if we look at this path, so clearly if x goes to 2, y does goes to minus 2, right? Then y does goes to minus 2. Okay. So along this path, y equals to minus x. So let's try to go along this path. So there are two cases now. So if I let it go along this path, I'll see that the numerator is fixed. Numerator goes to, the numerator goes to 4 minus 4. So 4 plus 4. So this goes to, the top goes to 8, but the denominator goes to 0, right? So clearly, in this case, the limit will be plus infinity or minus infinity, or it does not exist, right? So we want to formalize this. So we want to see if the limit exists or not. So notice the following: instead of taking this path, how about I take the path so along xy equals to minus 4, right? So if along this path, which is basically so xy equals to minus 4 is a parabola of this side. So in this case, consider the following. If absolute value of x is less than, so if you approach to 2 from this side, this means what? This is basically that absolute value of x and absolute value of y both are less than 2. Yeah. So in this case, we'll get, so if we look at this one here, we have x is less than 2 and y is essentially the value of y is bigger than minus 2. So we get what? We get xy is less than minus 4, right? Because we have x less than 2 and y greater than 2, so you multiply on both sides. So xy will be, so to do that, let's just change this in the following. We have xy is basically greater than minus 4, and this would imply that xy plus 4 is greater than 0. Yeah. So in this, along this line, we have, so along this blue curve, yeah. So along xy is greater than this, and this is greater than 4, and therefore along C1, so limit is going to be, limit as xy goes to 2 minus 2 along C1 is going to be 4 minus xy upon 4 plus xy. The top is going around positive 4, the denominator is going to infinity, denominator is going to 0, the whole thing has a positive sign, so this is infinity. Similarly, you can show that if this is your C2, limit of xy going to 2 minus 2 along C2 of 4 minus xy, 4 plus xy, the denominator is negative, the top is still positive, so minus infinity. So in this case, we say limit as x goes to xy going to 2 minus 2 f of xy does not exist. So this is a graph of your function on Desmos. So if I draw this graph, you will notice the following. So along line y equals to x, which goes, sorry, y equals to minus x. This is your line in the domain, all right? It's not a plane. We are restricted ourselves to D, which is the xy plane. So if you're approaching your function and 2 minus 2 is, so 2 is this point here. So 2 minus 2 is somewhere here. So let's mark that point. So with a different color pen, so 2 minus 2 is this point, right? Because why? Because this is your positive direction of x-axis, this is y-axis, and then the z-axis is above. So this is where your point is. Here, the y is, so if you're approaching to 2 minus 2, so y-axis you have minus 2 here, in x-axis you have 2, so the corresponding point, this point is your 2 minus 2. Now if you're approaching to, if you're approaching to 2 minus 2 from this side of the line, your function values are going up to, they're going to infinity. If you're approaching to, if you're approaching to xy along this part, so if you're approaching to 2 minus 2 from this side, your function values are going down to negative infinity. So in this case, the limit does not exist. So that's the idea here. So until now, we have one tool in our hand, namely, if we have to show that the limit does not exist, we just need to find two paths along which the limits are different. Okay. So these are the few limit laws. They are very similar to limit laws in function of one variable, namely if limit of f of xy as xy goes to ab is L, limit at xy goes to ab of g of xy is M, then the sum law applies, namely f of xy plus g of xy goes to L plus M. F of xy times g of xy goes to L times M. And f of xy divided by g of xy goes to L over M, where M is not 0. Otherwise, we have this limit. We have to do other calculations to find out what the limit is or to show that the limit exists. So, okay, so far we have one tool in our hand, namely that we create two paths along which the limits are different and hence the limit does not exist. So to show that the limit exists, of course, we have the definition, but we have the squeeze theorem in our favor. So consider the following. Let h of x, we want to basically find out limit as xy goes to ab of f of xy. So xy goes to ab of f of xy. We want to compute this. We want to find out what this is. Suppose that your f of xy is bounded by edge. So it's greater than equal to h of xy and less than equal to g of xy near ab. So near AB means along all points near AB in some neighborhood of AB, except maybe at AB. Note that at AB it may not be defined, right? Suppose the limit of this as xy goes to AB is L. Limit of this as xy goes to AB is also L. Then the limit of f of xy as xy goes to AB is also L. This is the squeeze theorem. So to use squeeze theorem, we have to be, let's see the following example where I will use the squeeze theorem. So notice the following. So we have y square is always less than equal to x square plus y square, no matter what, right? So this implies, and this is of course greater than equal to 0. So this implies y square upon x square plus y square is less than equal to 1, greater than equal to 0. Now, of course, to say that, I should say xy is not 0, 0, right? And at limit, we don't really care about what is the value of the function at that point, except that point. What is the value of the function in the neighborhood is the important aspect for us. So what do we get in this case? So this is going to be now multiplied throughout by x. So we get what? 0 less than equal to x. Now let's multiply by absolute value of x. So absolute value of x, y square upon x square plus y square is less than equal to absolute value of x. Now this is already 0, constant function 0. Now limit as xy goes to 0, 0 of absolute value of x equals to 0. Therefore, by squeeze theorem, limit as xy goes to 0, 0 of x y square upon x square plus y square, but with an absolute value sign, is 0. That is, if I write this same thing in a slightly different format, we have limit as xy goes to 0, 0 of absolute value of xy square upon x square plus y square equals to 0. But we have seen this property that if limit of absolute value goes to 0, then we have the inside must also go to 0. This is only true for going to 0, not for any other value, right? To 0. So we have to use squeeze theorem to prove this. Okay. Now comes the idea of continuity. So recall, what was the continuity for the function of one variable? So f is continuous, f of xy. F of x, let's make it clear that it's a function of one variable. So f of x is continuous at x equals to a if limit as x goes to a, f of x is equal to f of a. Okay. So this definition incorporates three things. First of all, that f of a is defined. Then limit as x goes to a, f of x exists. And third, that this limit which exists is equal to f of a. So the same three things should be valid for this guy. Yeah, namely one, f of ab is defined. Second, limit as xy goes to ab, f of xy exists. And third, that this limit of f of xy must be equal to f of ab. So when these three things happen, we say the function is continuous. Also, we say a function is continuous on set D if it is continuous at every point of D. So now we want to test for continuity at the following points. So let's test for continuity at 0, 0. So first of all, is f of 0, 0 defined? So f of 0, 0 is equal to 0 is defined. The first part is okay. Does the limit exist? So let's see. For that, limit as xy goes to 0, 0 of xy upon x square plus y square equals to limit as xy goes to 0, 0. Now let's take a path along y equals to x or y equals to mx. We get what? We get is equal to, instead of x, instead of y, I'm going to write mx divided by x square plus mx square, which I take x square common. So this is same as along the path. If x goes to 0, then y goes to 0, right? So you can write this as one-dimensional limit as well if you want to. You have x squared times m upon 1 by m squared times x squared. These cancel out. You get m upon 1 plus m squared. Yeah. So since this limit depends on path, it does not exist. And then since then the second condition is violated, right? So therefore f, so I should have corrected this. This is f of xy. Therefore f of xy is not continuous at 0, 0. Now I would like you to basically think about what other, so we in calculus 1 we had direct substitution property for the limit. Do those apply here? Under what circumstances do they apply? Okay, so that's an interesting thought. Let's look at the following problem. F of xy equals to xy square upon x square plus y square if xy is not 0 and 0, 0 otherwise. So if you look at this problem, we just now showed that, well, we did not exactly show that that limit is 0, but we had 2xy square upon x square plus y square. This is similar to, so let me change this problem because it matches with the earlier problem then. So earlier we showed that limit as xy goes to 0, 0 of xy equals to 0. And here we have, from this definition, we can see that f, this is same as f of 0, 0. Therefore, f is continuous at 0, 0. Okay, so it is indeed continuous. Now, question, what paths are we supposed to take? Yeah. So another example is f of xy equals to xy square upon x square plus y to the power 4. So if you look at this guy along y equals to mx, if we go to 0, 0, limit as xy goes to 0, 0, is going to be x times m square x square upon x square plus m to the 4, x to the 4, you take x square common, cancel it out. So you get limit as xy goes to 0, 0, mx upon 1 plus m to the 4 x square, and that is 0. So then the question is, does the limit exist? Because it exists along the path y equals to mx. Does the limit exist? And the answer is no. Note that in R2 or in D, there's not just lines. Yeah, y equals to mx is a line. So there's not just a line. There are a lot of different curves which basically approach to this point. Yeah, so if it exists, it must exist along any path, not just along the lines or along the paths which are lined. So consider the following path. So along y equals to or y square equals to mx, if we consider the following path, yeah, this is a reasonable path, right? Along y square equals to mx, limit as xy goes to 0, 0, f of xy is limit as xy goes to 0, 0. Now you can replace this by mx square upon x square plus mx the whole square, which is going to be take x square common, cancel it out. We get what? We get m upon, so x square times x square 1 plus m square. This is equal to m upon 1 plus m square. So since limit depends on path, since limit depends on the path, it does not exist or does not exist. D and E. So here's the take-home message from this, that if you want to show that the limit exists, showing it exists along the different paths is futile. Yeah. So you choose the path only when you want to show that the limit does not exist. If you want to show that the limit does exist, however, either use the definition or you can use the squeeze theorem. So these are the only tools we have in our hand at the moment. Okay. So this problem, I'll do it in the class. Now test for continuity at 0, 0 for this function. So again, now this is a function of 3 variables, but this is exactly, the concept is similar to function of 2 variables. So again, we'll deal with this in the following way. So now, when do we basically take the path game? When the degree of numerator and denominator are same, then you can think about path. Now that's not the only case, right? Here, in this case, the degree of numerator was 3, degree of denominator was 4. So that's not what always you do, but here the degree of numerator and denominator are same, then you can see a path, you can choose a path and then show that most likely the limit will not exist, okay, in those cases. So along, now in 3 dimensions, we can take y equals to mx and z equals to alpha x, where m and, or you can take the same, right? So also m also equals to y, z also equals to mx, where m belongs to R. We get limit as x, y, z goes to 0, 0, f of x, y, z is going to be limit as x, y, z goes to 0, 0. Now I can replace this limit by just writing x goes to 0, right? But it makes sense. If you're going along this path, then either you can directly write x goes to 0 or x, y, z goes to 0, 0. Now what will happen is your x will be x, of course. Y gets replaced by mx, x square plus mx the whole square plus mx the whole square. So we get limit as x, y, z goes to 0, 0 of m x squared common, x squared common from the denominator 1 plus m squared, which is going to be m upon 1 plus m 2m squared. So since this depends on the path, since the limit depends on the path, it does not exist. So now we want to basically prove, so we want to prove this. Now to prove this, I'm going to use the definition just to show you a technique. So what do I want? I want given epsilon greater than 0, there exists delta greater than 0 such that x minus 0 square plus y minus 0 square plus z minus 0 square root is greater than 0 less than delta. This should imply f of x, y, z. Again, here this should be z of x, y, of x, y, z minus L. Your L is, or f of a, f of 0, 0 is less than epsilon. And your f of 0, 0, 0 is actually 0. That is what is given to you here. So this is what we are going to do. So how do we go about it? So given epsilon greater than 0, we want to show that there exists delta greater than 0 such that x square plus y square plus z square less than delta implies absolute value of x, y, z upon x square plus y square plus z square is less than epsilon. Yeah, but this is same as, this thing is same as absolute value of x, absolute value of y, absolute value of z on x square plus y square plus z square is less than epsilon. So this is what we want to show. Yeah. So I'm using a definition in this case. Question, can we use squeeze theorem? That is something you can think about. Okay. So consider the following. Now, note that absolute value of x by definition, well, first of all, it's going to be greater than or equal to 0. This is going to be equal to square root of x square, right? Greater than or equal to 0 square root of x square, which is of course less than, because you have more terms here. This is going to be less than z square, right? So not only that, we have for all these guys, not just for x, but also for y and z. Similarly, we have 0 equal to y less than equal to x square plus y square plus z square. And similarly for z as well, absolute value of z as well is between these guys. So therefore, what do we get? We get x, y, z upon square root of, sorry, there's no square root here, right? This is not square root. So we have this thing upon x square plus y square plus z square is equal to absolute value of x, absolute value of y, absolute value of z divided by x square plus y square plus z square. Now this is less than equal to, so clearly this is greater than, sorry, we don't need that to be greater than 0, but this is less than equal to, each of x, y, and z is less than square root of x square plus y square plus z square. So this is going to be x plus square plus y square plus z square to the power 3 by 2, because you have 3 of them multiplied, square plus y square plus z square. That is equal to square root of x square plus y square z square. All right, so this is what you are, so this, you want this to be less than epsilon, right? This is what we want to be less than epsilon. This is what we need, So given epsilon greater than 0, if we choose delta equals to epsilon, then x square plus y square plus z square square root greater than greater than 0, less than delta, implies x, y, z upon x square plus y square plus z square is going to be less than epsilon. Following this chain, yeah, is going to be less than delta, which is less than delta equals to epsilon. So therefore, what do we get? Therefore, we got that limit as x, y, z goes to 0, 0, f of x, y, z equals to f of 0, 0. Therefore, f is continuous set. Okay, so this is using the definition. However, we are interested mostly, our interest lies in either taking a path to prove that it does not exist, or to use squeeze theorem to show that the limit exists and is equal to 0. So thank you for your attention.